Hi guys, so today we're going to do a video on the harmonic tremolo. So if you've been following the videos, we started with basic delay tutorial. From that, I came up with the idea to do the delay sequencer. And then I put a video up of that. And then after that, we went into setting up a dry wet control. And then we went on to setting like a pan control. And then, and this was introducing you to different modules like multiplication, switches, etc., different ways to get different tapers. And then we went on to sequencing, because sequencing was actually used in this delay sequencer. And then I went on to ring mod. So ring mod was the intro to pretty much modulation. The differences were between the different oscillators, and then feeding that, well, multiplying that with another signal to impart its waveform onto that based on amplitude, or being able to use the amp mod. So, and the reason I did that video was because it was leading up to doing the harmonic tremolo, which is what today's video is about. So this is the mono tremolo, but it's got everything you need to be able to get a nice moody mono harmonic trem. But if you want to do stereo, you can just basically duplicate this network and then feed the left into the left and the right into the right, and you can have that going out over here. But stereo is not the subject of this video because that gets a bit complicated. Obviously you can just use stereo source with the duplicated network, but you're not going to have the harmonic modulation happening in stereo, if you know what I mean. So the first thing we've got happening here, if we look at the signal, we're going straight into the mod IIR. This one is for the low signal, and then this one is for the high signal. So obviously if you look at a harmonic tremolo, imagine the full frequency bandwidth. You got from 0 up to 20 kilohertz, right? There's going to be a crossover point, and let's say for example that's at 1 kilohertz. So you're going to have a low pass that's going to do everything up until 1 kilohertz, and then you're going to have a high pass that's everything above 1 kilohertz. Or 500 hertz, whatever that crossover point is set as. And then they're basically going to taper down to infinity, but they're going to cross over each other. And importantly, they're going to be out of phase with each other. Okay, so that's how we get the phasing effect. And then the low pass is going into an amp mod. And then the high signal is going into an inverter. This is how I do it. I mean, there's several ways to do this. You could put it into a multiplication module, etc., and then you're basically multiplying by -1. So this is just scaling it to -1. But it takes a control signal input, so it's going to be out of phase with the low pass. They're each going into their own amp mod module. And then I'm taking it into a mix module where you're basically just mixing two signals together. And there's a mod high cut. That's just to kind of roll off some of the highs. It's quite a nice analog sounding mod high cut. And then finally into a gain module. And I put the gain module in because when you start to increase the depth on the harmonic tremolo, then because things are going out of phase, because things are tremoloing, it kind of, the level seems to drop off just a little bit. So it's a way to compensate for that. And ideally within a proper algorithm, you would have it so that the depth, as the depth is increased, and the gain would automatically be increased as well. But that's not the focus of this video. Okay, and then from the output of the gain is going into the ADC left and right. So you're going to hear it out of both the left and the right speakers. And then, how are we modulating the signal? So this all comes down to this H9000 oscillator. So if I select this oscillator, on the right hand side here, you can see the details for it. I'm not doing anything with the trigger, I'm not doing anything with the mod input. And the mod input on this oscillator is to modulate the waveform. So you could basically have this oscillator set to be a triangle, and then you could feed the mod input with a sine wave, and then you're going to kind of get a mix of those two. So you're kind of multiplying those signals together. And you can set the mod amount, but I'm not using either of those. So trigger not used, mod not used, mod amount not used. So what we are doing is we're setting the frequency. We're setting the frequency using this tremolo rate module. Okay. And then we're setting, the waveform. So we're able to pick which waveform we want. Okay, so that's happening over here. So we've got waveform, sine, triangle, square, peak, ramp. And I'm putting that into a table, but actually I don't need it. I have another version of this harmonic tremolo where I've got another oscillator. I'm using the analog LFOs. And in order to do that, I need to use a table, and there was some other stuff I needed to do. So actually I just left the table in. So we're only using these waveforms, but the H9000 oscillator has loads of them. So you could use all of these. But some of them are more useful than others. Some of them can get a little bit clicky. So what I mean is they've got really sharp edges to the waveform. So, and when you increase the speed of that too much, then things get a little bit clicky. So it's probably better to do some of those with additional modules like the slew module to slow the rates of change at that peak point, just to kind of round it out a little bit. Then we've got a duty cycle of 0.5. That's basically just the midpoint. I didn't see any reason to change that. And this phase, offset, and polarity. But I'm not using either of these, right? The whole point of a harmonic tremolo is that you've got the low signal, which is the low pass signal, and you've got the high pass signal. As the one is going up, the other one's going down. Basically like a seesaw. So imagine a seesaw, you're going to have the one going up while the other one's going down. As they meet in the middle, the crossover point is going to be out of phase with each other. Okay, and that's basically what the harmonic tremolo is doing. And these filter modules, they're the ones that allow you to separate those signals and then doing the phase inversion so that you can get that out of phase sound, a really moody kind of setup. Okay, so it's quite a simple little network, but there's quite a few nuances with how the modiir works. And my initial setup was actually pretty close, but it wasn't accurate. I had to seek some advice from Eventide about how this works. So the documentation is pretty light. It doesn't tell you half of the things that are possible. It doesn't even tell you about the mod frequency input. It's got a minimum of -1 and a maximum of 1. So my assumption was, okay, well, -1 is probably 0, and then 1 is going to be 20 kilohertz. So you got that range, 2.0 value range in which to basically go and sweep the entire frequency spectrum. Okay, but that's not how it actually works at all. From 0 to 1, you've got a range of 18 hertz up to the Nyquist of the sample rate. So if you're working at 48K, then it's going to be 24 kilohertz is going to be the range. So from 0 to 1 is 0 hertz up to 24 kilohertz, right? But 0 is not the lowest that this modiir can go to. It actually, the lowest it goes to is 18 hertz. So as you get below 18 hertz, it's just not going to go any lower. So nothing's going to happen. Okay, so that is the important nuance of this modiir. And if you want to change the sample rate, then this range changes. So, and this is actually the same module that is used for Harmodillo. And that's one of the reasons why we don't have it for the H9000 yet, is because it needs a bit of redevelopment work to get it working at various sample rates, because the H9000 can do lots of different sample rates, whereas the H9 is just working probably 48 kilohertz. I don't actually know. So they only really need to have one setup for that. But for the H9000, there'll need to be some variations to that to deal with the sample rate changes. Okay, so that's quite an important nuance to modiir, but I built that in here. It's not actually 100% accurate, because when I was chatting to the guys about this, you've got frequency warping. So what that means is that you've got this range of 0 to 1 where you've got all these different frequencies that need to be represented. So from 0 to 1, you're going from 0 to 24 kilohertz, okay? Or in the case of 96 kilohertz, you're going to go from 0 right the way up to 48 kilohertz. So I created a spreadsheet. It starts at the top here with sample rates. So if you're 44.1, if you're 48, if you're 88.2 or 96, then these are the modulation values that would apply. So at mod val 0 for 48 kilohertz, they're all going to be 0. But at mod val 1, this one's going to be 22.05, this one's going to be 24, this one's going to be 44.1 and 48,000, which is, it's obviously a range beyond our hearing. So if we wanted to work at 96 kilohertz, then this range from 0 to 1 gets even smaller. So if you want to have a range of 0 to 20 kilohertz, your max value for mod val needs to be 0.416, and then that's going to be 20 kilohertz. Okay? And then what I figured out was for each 1 hertz, that's going to be the increment. But there's actually a simplified way to do this. If you want to work out what your frequency is going to be, you do the frequency that you want. So if I want 500 hertz, for example, it's going to be 500 hertz divided by B6. Okay? And that is essentially the frequency of 500 hertz divided by the sample rate divided by 2. So it's basically frequency divided by the Nyquist. Then this is the value at 500 hertz and this is the value at 20 kilohertz. So when you look at the 96 kilohertz, if I want to represent 20K at 96 kilohertz, my mod val value needs to be 0.41666667, etc. Mod IR really deserves its own video. But what you've got here, you can apply sections. So this is the max amount of sections you want to be available to the module. And then down here is where you're actually setting what the module is. So this is a specifier, okay? It's just saying, well, if you set that to 10, and then down here, you can apply a control input to control the sections. Now I've just got this set to a 1. And what this 1 is going to do is set it to a 4th order low pass, and this one's going to be a 4th order high pass. Now, if you go and change these sections and you make these filter slopes even steeper, it does apply a phase shift to a signal. Unless you're using a linear phase filter, you're going to get some phase shifting. What we're doing here is we're inverting the phase over here. And if we set slopes here and the Q value is incorrect to create a kind of flat frequency response, then you're going to get phase artifacts. This setup over here is a Linkwitz Rayleigh crossover. So when we've got that Q value and these two set up in parallel, and when the crossover is at the exact same frequency point, but I don't know enough to be able to explain that stuff. I managed to get that Q value from Eventide actually, so they were really helpful. The algo looks a little bit different now because I came in and simplified a few things and added a couple of other functions. Taking the sample rate, then dividing it by 2 to get the Nyquist, then multiplying it by 1,000 to actually get the hertz, because this is going to be a kilohertz output, then divided by 2 to get the Nyquist, but that's still in kilohertz, and then to multiply it to get into hertz. Going back to the numbers document, and as I've already shown you the video of how I got to my calculations, this is the Nyquist, which is the sample rate divided by 2. Okay, and this is the math that we're trying to achieve here. Frequency divided by sample rate, which is divided by 2. Okay, so now it's frequency divided by that. If I go into that, so it's A8 divided by the Nyquist in hertz, and gives you this. So at any one point in time, for any one of the frequency values that we want to figure out, we're simply just doing that math. Okay, so it's going to be the frequency divided by the Nyquist. Okay, and that tells us what the modulation value needs to be. So going back to this, here it is, sample rate, maybe 48K divided by 2 to get 24K, which is the Nyquist, multiplied by 1,000 to get the hertz value. The output of this is going into these two modules. Okay, so this module is used to calculate the main crossover frequency. So crossover frequency is going into this divide module, okay, in the top here, and then we're doing the frequency divided by the Nyquist in hertz. We're doing this final math over here. And that output, and we're then converting this from a control signal to an audio signal, and then we're putting it into a slew module. Now over here, we're pretty much doing the same. This is the overlap frequency. So within the UI, you can see what that looked like. There was an overlap value, and that defined based on the crossover, how much do you want the high pass and the low pass to overlap each other? Because by default, if you set this to 0, you can have the high pass and the low pass set at the exact same frequency, which should give you a flat frequency response from 0 right the way up to 20 kilohertz, based on the configuration that we've set up. This crossover frequency is then dividing by the Nyquist in hertz, converting it to an audio signal, putting it into a slew module, and then going into the high pass mod IIRQ. Okay? I'm doing some calculations here. I won't get into that just yet. This overlap is to say, well, minus 200 to plus 200. So do I want to overlap by 200 hertz? Or do I want to set the overlap negative 200, which means that they're overlapping very slightly now. You're going to have like a hollow in the middle. So if I set this crossover to 2000, when this overlap is plus 200, the low pass is going to be set to 2200. So they're going to be overlapping by 200 hertz. But if I set the overlap to negative 200, then the low pass is going to be set to 1800 hertz. And then you get different sounds with that. You get something a little more mid-range if it's plus 200, or you get something that's a little more hollowed out at negative 200, where the signals are crossing over. You're going to get a little bit less phasing, but it's still quite a nice sound. Okay, and then the overlap is going into an adder where you're basically taking the crossover and you're adding the overlap value. So if this is set to 2000, then obviously, and this is set to 200, then you're going to get 2200. Whereas if this is set to negative 200 or anywhere in between, you're going to get the crossover value minus 200, because it's going to be plus negative 200, which is going to essentially minus. And then we're dividing that over here by the Nyquist in hertz. Once again, converting that to an audio signal and then going into a low slew module. Now, the reason we put a slew module in is if I go directly from here into the mod IIRs, okay, then what's going to happen is when we're changing the frequency, we might get a little bit of clicking because we're going to be jumping to different frequency values. So what the slew module does is it slows the rate of change. Now we're only doing a very subtle slowdown, like just 2 milliseconds. So if there's a peak, it's basically just going to slow that down a tiny bit, the rate of change, which prevents the clicking. And I'm doing that for both the high and the low. So just to talk a little bit about the amp mod. So when we were setting up the amp modulation for the ring mod algorithm, that was quite simple. We were simply taking the oscillator, and then we were feeding that into the amp mod, into the modulation input, basically multiplying that by the actual input. So if you were taking a sine wave, a rate of 300 cycles a second, then you're going to impart that frequency upon the audio signal, and that's how you get all those dissonant types of sounds, right? And then that's basically going to be 100% that you're applying of that modulation. But anyway, when you're doing this harmonic tremolo, you do want to apply your offset. So how much do you want to modulate the signal? For this low pass amp mod, we've got the input, which is the mod IIR input, which is your audio signal to represent the low frequencies. Then you got the modulation input, which is the oscillator input. And then you got the mod amount set by the trem depth. So if I alt click on that, you'll see that that's going into the mod amount in the amp mod. And I've set this to 1%, okay? Because mod amount from -10 to +10, but basically you can achieve everything you want within a -1 to +1 range. Everything beyond that is basically amplifying the modulation input. And I actually just found that really confusing, to be honest. And when I initially implemented a harmonic trem, like when I first got my H9000, the amplification was actually causing me a lot of headaches. So anyway, you just really need to work within a 0 to 1, unless you find maybe that your signal source for modulation is very weak. So I could use a percent knob. So if you watch the other videos, we discussed a percent knob. I've set the min to 0, the maximum to 100. It's going to output from 0 to 1, even though you got your min of 0 and your max of 100. Okay, so if I've got the set to a default of 92, that's going to be 0.92 that this is going to output into the mod amount. And then what I'm doing is I'm subtracting. So I did show in the previous video about how we invert something. And there's a few ways to do it. You could either use a switch or you could use a table. And in this case, I'm using a subtract module and I'm taking 1 minus the trem depth. So if I set the trem depth to 10%, okay, that's going to output a 0.1. And then I take that, 1 minus 0.1 is going to give me a 0.9. And then that's where this is going into the offset. What happens is if you set that to a 1, you're basically modulating at 100%. So then your harmonic trem is going to be 100%. But if I start dropping this to a 0.9, okay, or a 0.8 or a 0.1, for example, what's going to happen is we're going to get less modulation, but we're also going to get less level. So if you imagine that the oscillator is going from 0 to 1, 0 to 1, you know, whatever waveform it's doing, whether it's triangle, the bottom of the triangle is going to be 0, the top point of the triangle is going to be 1. If we set the mod amount to a 0.9, then we're basically going to end up having the triangle going from 0 to 0.9. And what if we set that to a 0.5? So that's essentially half. Then you're going to have the triangle only going halfway up the waveform. And because you're multiplying those signals together, you're lowering the overall level of your output signal. But what you wanted to do is apply offset to go from 0.5 to 1, 0.5 to 1. If you set that to 0.5, it's basically going to add a 0.5. So then you'll have the triangle going from 0.5 to 1, 0.5 to 1, etc. And that's what this module then does over here, the subtract. So 1 minus the tremolo depth, and then we end up with an offset value. So for my default here, I've set this to 92, which is going to output a 0.92. And then when I do the subtract 1 minus 0.92, we're ending up with a 0.08. If you used a multiply module here, which is essentially what an amp mod is doing, you don't have the offset value. Basically, your mod amount is going to be, 100%, unless you apply other modules in the middle. And then you take this amp mod out and we're mixing them together. Mod high cut, you can pretty much ignore what these are doing. You could just take that out from the mix, and then you would essentially get tremolo just of the low signal and just of the high signal, and you're mixing them together like the seesaw effect. When the bass is high, the treb is low, and then when the treb is high, the bass is low, seesawing up and down like that. And with a crossover in the middle, that's where you get the out of phase vibe, and that's the harmonic tremolo. So this is going to look slightly different now, because what I've done is I've added in a slew module between the oscillator and the modiir. So what this slew module is doing is slowing the rate of change of the oscillator just by 5 milliseconds, positive and negative. So when it's changing to a positive value, it's going to just slow that rate of change by 5 milliseconds. And the negative slew is going to slow it down by 5 milliseconds as well. And why do I do that? Well, even at moderate speeds, you're going to get quite a bit of clicking, okay? And that applies to both the square wave and for the ramp. The slew module essentially slows the rate of change within a square waveform. It's going to round out those square edges a little bit. It's going to affect the triangle ever so slightly, but it's not really going to be perceptible. Okay, and what I didn't yet discuss was this oscillator is going directly into the slew module, and this slew module is controlling the modulation for the low pass signal, right? But what do we do about the high pass signal? So from the slew module, I'm going into a delay module. And the delay module is then setting up the phase, because if I set this oscillator to go directly from the slew into both of these amp modulators, they'll be modulating in the same phase. The whole point of a harmonic trem is that you've got that seesaw effect. So when the low pass signal is high, then the high pass signal is low, and then vice versa. So what the mod delay does, it allows you to define a phase offset for the high pass signal. Now, if you think of that in terms of degrees, you've got 0 to 360 degrees. At 180 degrees, they're going to be 180 degrees out of phase, so you're going to get that perfect seesaw effect. But by having this, you can set it anywhere between 0 and 360 degrees, so you can get different phases for that seesaw effect. And you can get some different sounds out of that. So that's basically what the mod delay module is doing here. And that value is being defined over here. So I've set it to be in degrees, from 0 to 360 degrees with a default of 180. And what we do is we put that into a multiply module, and then we're multiplying that by 0.002777, etc. And then we're multiplying that by the rate to milliseconds divide. So what I've done here is I've taken the tremolo rate, okay, and I've put that into a divide because I want to basically take the rate and then convert that into milliseconds. Okay, because rate over here is going to affect directly the oscillator, and that we're dealing with in hertz. But if I want to understand how things work in the time domain for based in milliseconds for the mod delay, because the mod delay takes in a value which defines the milliseconds, okay, then we need to do that. So we can go 1,000 divided by the rate. If we go 1,000 divided by 1 hertz, then you're going to end up with 1,000 milliseconds. But if you go 1,000 divided by 2 hertz, then you're going to have 500 milliseconds, etc. So that is the math for that to convert from hertz into milliseconds. Now, I'm using the mod delay here, but the oscillator itself does have a phase offset parameter. So I could have had 2 oscillators, and then the second oscillator just could have had a different phase offset. Okay, and I could have triggered them in the beginning and then had a different phase offset. But when I changed the phase offset, I didn't actually notice any change. Now, I could have been doing something wrong, but it doesn't matter. You know, I quite like doing the mod delay anyway, because when I did try and trigger this to do the phase offset, then you would get some clicking because things would be switching. So just to keep things simple, I basically just used the mod delay. And what I like about using the mod delay is that as you change the mod delay, there's no clicking or anything. And I just had to do a little bit of math, but you know, using 2 oscillators would make a lot more sense. And there's ways to go about that, but I guess this is just a little bit more continuously changeable without having to re-trigger the oscillator, and also lower on the CPU actually. Okay, so how do we get the mod delay value? Because we've got a rate which is defining the oscillator rate, okay, and that's going direct, so that's going to be, say, 2 hertz is going to be 2 cycles a second. So how do we figure out what the delay value is to apply the offset? So once again, I've done it within a spreadsheet. So it's phase offset to millisecond delay. So the first thing I did was I came up with what is the phase increment? So I want to work within a 360 degree range because people understand that as degrees offset. So 1 divided by 360 is going to give me an incremental value. So if I set the phase to 180, it's going to be 180 multiplied by that. And the reason why I go like this is because if this was 360, then basically the value is going to be 1. Okay, so 360 multiplied by that is going to give me a 1. And then 1 multiplied by the rate in milliseconds is going to give me that rate in milliseconds. So that's 1 full cycle. So what we're doing here is we're doing 1 divided by 360 to get the increment. And then I'm specifying, well, what is the rate in hertz? So we can change this value. This could be 2, 10, 12, it doesn't matter. And then we just want to understand, well, what is the rate in milliseconds? The rate in milliseconds is 1,000 milliseconds divided by the hertz. So at 2 hertz, it's going to be 500 milliseconds. And then we need to know, well, what is the phase value? And this is the result. First going to do the calculation in the brackets. So it's B34 multiplied by B30. So B34 multiplied by B30, so 180 degrees multiplied by the increment value, which is going to be a 0.5. Okay, and then we're multiplying that by B33, which is the 500 milliseconds, and that gives us 250 milliseconds to get a 180 degree out of phase value. So if I go and change this to 4 hertz, you can see that's going to get smaller. Or back to 2, And what phase do we want? So if I want to set that to 0, then obviously the delay is going to be 0. So the oscillator is going to output exactly the same to both the high pass and the low pass amp modulation. Okay, or anywhere in between. 270, you're going to get 375. Okay, so that's all I'm doing here. And then this offset is defining, well, what is the degree phase offset? So that is going into this multiply by the increment. Okay, and that increment we get by 1 divided by 360. And then from there, we're going into this multiply module. And this multiply module is multiplying the output of this increment. So if it's going to be 180 degrees, it's multiplying by the increment, which is going to be 0.5. So it's going to be half of whatever this millisecond value is. So that's all that's doing. So that's multiplying 0.5 by this rate to milliseconds. And then that result is output into the mod delay. Just to go through that math, you're finding out, so this is the result. So if you're going to do 2 Hertz, then each cycle is going to be 500 milliseconds. Equally, if that was set to 1, then each cycle is going to be 1000 milliseconds. Okay? And then we're taking the phase, which is going to be 270. So we're multiplying the 270 by the increment. Well, let's just keep this 180 to keep it simple. So 180 multiplied by that is going to give us a 0.5. And then we're saying, well, what is 0.5 of the 1000? And then that's going to be 500. And then we're outputting that into the mod delay. And then the mod delay is then going into the high pass amp mod. Well, thanks for watching. I hope that's useful, and download the file and have a listen to it. And I think it's a beautiful harmonic tremolo. It's amazing just by matching the sections to the Q value, setting these values correctly, you basically can get a flat frequency response across the entire spectrum where both of these are set to the exact same frequency. And I just want to do a shout out to Eventide. They've been amazing supporting and helping with the H9000 and Vsig and bug fixing things. And I've had a few issues, and they're always there to help. Shout out to David Bailey's, Joe Bamberg, Peter McCulloch, and Woody, and anybody else who's jumped in to help, and obviously the guys over at Gearsluts. It really is helpful to have a better community to be able to talk about these things. I mean, particularly it's necessary to be able to have Eventide's help, because where else are we going to get information about how modiir really works, But anyway, I hope that makes sense. I'll share this file and you guys can test this on your H9000s.